What if I told you that the laws of physics only work the way they do because of the emptiness around you? But here's the twist. That emptiness isn't empty. Not really. It's buzzing, alive with invisible fluctuations. Every moment, even in perfect vacuum, space itself crackles with electric and magnetic jitter. These are called zero-point fluctuations, and they're the reason why the speed of light is what it is, why electric charges behave the way they do, why magnets work at all. This underlying structure, this hidden order, is described by what's known as U1 symmetry. It's one of the simplest forms of gauge symmetry in physics. It means the electromagnetic laws are the same no matter where you are or what direction you're facing. This is why a light beam travels the same way in New York as it does on Mars. But what if you could break that symmetry? Not destroy it, but bend it, condition it, create a localized bubble where the vacuum behaves differently. This is where S2 comes in. It's a higher form of symmetry, a more complex kind of order in the fields that shape our world. And it opens the door to something radical, engineering the properties of space itself. That's what this study is about. Using specially wound coils, toroids, to potentially induce an SU gauge field bubble inside the lab, a pocket of spacetime with its own altered behavior. A place where electromagnetic forces don't follow the usual rules, a platform for experiments that could one day lead to new propulsion methods, advanced sensing, or even field-based shielding. This isn't science fiction. It's a blueprint. Imagine creating a region of space where energy flows differently, where magnetic fields do strange, unexpected things, where the fabric of the vacuum itself might carry information or power or force on demand. In this video, we're going to walk through how researchers tried to do exactly that, what they found, how it works, and what it means for the future of physics, and maybe for technologies that haven't even been invented yet. Welcome to the frontier. Imagine you're throwing a ball. Whether you toss it to the left, right, or straight up, the rules stay the same. Gravity pulls it down. It curves through the air. You can count on it. That consistency, that's symmetry. In physics, U1 symmetry is one of the most basic kinds of symmetry nature has. It's the reason the laws of electromagnetism, the ones that make your phone work, power your house, and let you microwave leftovers, work the same no matter where you are or which way you're facing. U1 isn't just about electricity and magnets. It's built into the fabric of space. It says that when you rotate something or move it around, the underlying physics doesn't change. Your coffee still heats up the same way in the microwave, whether the machine is facing east or west. It's also the reason light travels in straight lines, why electrons stay in atoms, and why you can build an electric guitar or a GPS satellite and expect both to function exactly as designed. U1 gives us a stable, reliable universe. But here's what makes it wild. All of this order, the consistency of light, charge, fields, emerges from what seems like chaos. The vacuum of space isn't empty. It's a seething sea of tiny, jittering fluctuations called zero-point energy. These random tremors are always there, even in total darkness and absolute silence. And from that background noise, U1 symmetry gives rise to order. It's like finding rhythm in static. So every time you flip on a light switch or hear a radio signal or charge your phone, you're tapping into the calm rules drawn from that deeper quantum buzz. U1 is the base layer, the operating system of reality. It doesn't just describe how fields behave, it enforces that behavior everywhere. And now we're asking, can we step beyond it? What happens if we create a space where the vacuum follows different rules? That's where SU2 comes in. But more on that in a bit. So now that we know U1 symmetry is like the universal playbook, the rule book that everything from light bulbs to gravity quietly follows, let's talk about what happens when you bend that rule book. Not break it, just rewrite a few pages. Physicist Terrence Barrett proposed something bold, that under the right conditions, you could create a different kind of symmetry inside a small pocket of space, a kind that doesn't follow the neat, predictable rules of U1. This higher symmetry is called SU2-2. Think of U1 like a single gear spinning smooth on its own. SU2 is more like a pair of interlocking gears, more complex, more connected, and capable of motion you just don't get with one. Why does this matter? because SU2 fields can do things that U1 fields can't. In a U1 world, electric and magnetic fields are separate but related. One can cause the other, but they stay in their lanes. In SU2, those lanes start to blur. Fields can twist together. Potentials, those ghost-like precursors to actual force, start behaving like real, physical stuff. Barrett theorized that if you wound a coil into the shape of a torus, a kind of 3D donut, and ran alternating current through it just right, you could condition the surrounding space. Not just send out a signal, but actually reshape the vacuum in that area into an SU2 bubble. This isn't about sending out normal electromagnetic radiation. This is about changing the medium itself. Like turning water into jelly, suddenly the rules of flow and pressure change entirely. And the toroid? That's the tool, a precise resonant shape that can stir the vacuum into this higher order if tuned to the right frequency. The idea is, create the right geometry, use the right current, hit the resonant frequency, and the vacuum might just reorganize itself into something new. In the next part, we'll look at how researchers actually built these coils and what happened when they flipped the switch. Let's get practical. If you're curious enough, you could actually build one of these field conditioning devices yourself. It's called a Countra-Wound Toroidal Helical antenna. It looks like a donut-shaped coil of wire, but with a very specific twist. Literally, you take two wires and wrap them around a torus, like copper spaghetti spiraling around a foam donut. But the secret is, the wires are wrapped in opposite helices, like two snakes twisting around the same ring, each spiraling in the opposite direction. This configuration is known as a caduceus winding, named after the staff of Hermes with its twin snakes, and it allows for a very unusual mode, the current opposing configuration, where equal and opposite currents flow through the wires. What you'll need: core material, a donut shape made from non-ferromagnetic material, like styrofoam, plastic, or wood. Do not use iron, ferrite, or any magnetic core. Magnetic cores distort the field structure and break the subtle balance required for forming SU2 phase fields. Wire. 2 equal lengths of enameled copper wire, 22 to 26 ABG works well. Pick 2 different colors to keep track of your windings, say red and white. Signal generator. You need to sweep across a wide range. 400 kilohertz to 110 megahertz is a good start. An RF function generator works. If you want to get serious, tools like the HP 4195A impedance analyzer let you detect resonant frequencies precisely. Optional tools, a magnetic field probe, oscilloscope, or even a simple handmade pickup coil can help you detect field effects. Josephson junction detectors would be ideal but are complex and expensive. How to build it. 1. Prepare the core. Cut or purchase a torus made from styrofoam or other inert material. A typical size might be 12 inches outer diameter and 6 inches inner diameter. 2. Wind the wires, double helix style. Start winding both wires around the torus in a helical pattern, but make sure one wire spirals left-handed and the other right-handed. You're creating a DNA-style double helix around the donut. 3. Spacing matters. Keep the spacing even and tight. Barrett notes that tightly wound coils show more resonant behavior than loose ones. 4. Connect the leads. Each wire has 2 ends. Connect them in one of 2 ways. Current adding mode. Both wires carry current in the same direction. Current opposing mode. Each wire carries equal current in opposite directions. This is the one Barrett emphasizes for conditioning the vacuum. 5. Sweep the signal. Use your function generator to slowly sweep through the frequency range. You're hunting for resonance points, frequencies where the coil rings and starts to interact strongly with its own field. What's happening here? When you hit a resonant frequency in the current opposing mode, the magnetic fields from the 2 wires cancel inside the coil. But outside, things get weird. You start forming standing waves, not just in the B field, but in the underlying vector potentials. These A fields are normally invisible in U1 electromagnetism, but in this configuration, they become structured and possibly physical, what Barrett calls differential phase factor waves, or U fields. If all goes right, you're not just transmitting energy, you're restructuring the vacuum in that little donut-shaped zone. The space inside and around the coil is no longer playing by U1 rules. It's entered a different regime of symmetry, one where new types of field interactions can happen. That's your SU2 bubble. Next up, what happened when researchers actually built these coils and measured the results? Let's see what they discovered. Let's talk about what actually happened when these toroidal coils were built and tested. The results weren't just interesting, they were weird. The kind of weird that makes you double-check your instruments, then double-check your understanding of physics. Researchers built 4 different toroidal coils, some big, some small, all with contra-wound double helices. One of them was shaped like a teardrop. When they ran alternating current through these coils and swept across a wide range of frequencies, anywhere from 400 kilohertz to over 100 megahertz, they found sharp resonances. At specific frequencies, the coils didn't just react, they sang. Strong, narrow frequency bands where energy buildup spiked dramatically, especially in the current opposing mode. Here's the strangest part. In the current opposing setup, where the magnetic fields inside the coil should cancel out, there were still measurable magnetic fields outside. That's not supposed to happen. In standard U1 electromagnetism, 2 equal and opposite currents should produce a zero net field. But outside these coils, strong fields, sharp gradients, standing waves. It's as if the vacuum around the coil had been stirred into a new state. And then there's the teardrop-shaped torus. Unlike the symmetrical donut coils, this one focused its field in a specific direction. At one of its resonant frequencies, the magnetic field energy shot forward, not spherically, not randomly, but like a beam. That might sound small, but it's a massive deal. Because in physics, if you can create a directional force without pushing off anything, no propellant, no recoil, you're stepping into the territory of field propulsion. This is the beginning of engineering asymmetry into the vacuum. That's not a joke. That's real experimental evidence suggesting you might be able to create a localized region of space where the vacuum itself is lopsided, where the geometry of the coil changes the way space responds to electromagnetic fields. It's like crafting a little wave in the ocean and riding it forward without paddling. That's the kind of mechanism that could lead to new types of propulsion, non-Newtonian, field-based movement, potentially even in a vacuum. It's one of the holy grails of advanced physics research. If verified, it means propulsion without reaction mass, without burning fuel. Just field manipulation. Want to try this yourself? If you're thinking of replicating some of these effects, here's how you can start experimenting. Build a toroidal coil using non-magnetic materials, styrofoam or plastic for the core. Use dual copper wires with opposite helical winding. Drive it with a signal generator and sweep from 400 kilohertz to 110 megahertz. Test both current adding and current opposing modes. Use a magnetic field probe to look for resonant spikes, standing wave formations, field behavior differences between modes. Try changing the geometry. Flatten one side of the torus into a teardrop shape and repeat the test. Watch what happens to the field directionality. If you want to go deeper, try putting magnetic sensors at multiple distances from the coil. Measure how the signal falls off. Look for deviations from the normal 1R squared behavior. Record directional emissions, especially in the teardrop design. You won't be measuring SU2 fields directly yet. That would take high-end tools like Josephson junction arrays. But you can still detect symmetry breaking, directional bias, and strange field patterns, signatures of something new happening. The implications of this are enormous. We're talking about direct manipulation of space-time conditions, right from your bench. If the field around these coils can be conditioned into higher symmetry states, if SU2 bubbles are real and controllable, then the door opens to technologies we haven't even imagined. Energy transfer, advanced sensing, possibly even inertia manipulation. All of it starts with a coil and a question. What if empty space isn't